Hi, my name is Irene.
And my name is Joy.
For the 2023 STEM Fellowship Big Data Challenge, we investigated the effects of greenhouse gas emission-induced thawing permafrost on housing safety. In this presentation, we will be going over the contents of our paper. It will be split into 4 sections. 1, introduction, 2, materials and methods, 3, results and discussion, and 4, conclusion. Everyone deserves the right to safe housing, but not everyone has access to safe housing. This year's Big Data Challenge puts an emphasis on the United Nations Sustainability Development Goal 11, which calls to make cities and human settlements inclusive, safe, resilient, and sustainable. This study focuses on how greenhouse gases could possibly affect permafrost, its impacts on housing safety, and proposes a few counteractive measures. Globally, there are many communities developed on top of permafrost, especially in the Arctic region. Historically, this posed less concerns because the permafrost remained in its frozen state year-round. However, with climate change on the rise, permafrost thaw has been steadily increasing. This poses a serious issue for houses built on top of these areas, as melting permafrost can pose many dangers, including, but is not limited to, increased risk of landslides, coastal erosion, contaminated bodies of water, and damage to infrastructure, including foundations and drywall. Additionally, communities in the Arctic are typically isolated, with limited access to resources such as food, reliable internet, and medical services. These factors combined further contribute to the safety imbalance between communities on permafrost and permafrost-free communities. Throughout our research, we use a few acronyms to make our paper easier to understand and read. Greenhouse gases, GHGs, are composed of any gas that traps heat in the atmosphere. This includes carbon dioxide, methane, nitrous oxide, and more. Global warming potential, GWP, is the measure of a greenhouse gas's ability to trap heat in the environment by comparing it to 1 ton of carbon dioxide in a time period of 100 years. The larger the GWP, the more capacity a GHG has to warm the Earth. GWP helps researchers make comparisons between different GHGs. We obtained GWP values from government resources. For this study, the GWP of carbon dioxide is defined to be 1, which is standard, the GWP of methane is 25, and the GWP of nitrous oxide is 273. Shared Socioeconomic Pathways, SSPs, are projected socioeconomic global changes up to the year 2100, defined by the Intergovernmental Panel on Climate Change, which is an intergovernmental body of the United Nations. Using SSPs, possible future GHG emissions and climate scenarios can be predicted. There are 5 SSP scenarios, which can be ranked on challenges for mitigation and adaptation. The mitigation axis determines how difficult it will be to mitigate climate change, while the adaptation axis rates how difficult it will be for the climate to adapt. The 3 scenarios that we focus on in this study are as follows. SSP1, sustainability. We take action against climate change and choose sustainable practices to reduce GHG emissions. Number 2, middle of the road. There are a few changes from the past as we continue to move forward. Development is unequal, with some countries advancing and others falling behind. SSP5, fossil fuel development. Society prioritizes technological development over sustainability, leading to advancements in multiple fields of study. However, the environment suffers and climate change worsens. Each of these scenarios can be further divided into pathways based on the radiative forcing values by year 2100. Radiative forcing describes the amount of excess energy trapped within the Earth's climate system due to the variation of climate change factors, for example, GHG emissions. When naming an SSP pathway, the scenario number comes first and is then followed by its radiative forcing value. For example, SSP1 2.6 indicates that it is scenario 1, sustainability, with a radiative forcing of 2.6 by year 2100. When we conducted a literature review, we noticed one important detail. Other papers did not focus on connecting melting permafrost to SSP scenarios. Our research is more detailed and provides a more nuanced approach to the problem. Our study draws connections between housing safety, GHG emissions, permafrost temperatures, and the many possible futures that depend on our approach to climate change. Data was collected in four different categories. First, we gathered data on historical permafrost temperature, which was taken from the US Environmental Protection Agency, EPA, and Pangea. It recorded the annual average permafrost temperature. Next, data on GHG emissions was taken from the Global Carbon Project and Climate Watch. These datasets tracked the total annual emissions of each respective gas, which included our three focuses: carbon dioxide, methane, and nitrous oxide. Additionally, global warming potential values were collected from government resources. Finally, data on future projected GHG values was collected from the International Institute for Applied Systems Analysis. It contained the respective emissions of GHGs in different SSP pathways.
Let's take a closer look at the permafrost data. The dataset contained the temperatures from 24 unique boreholes located globally. The time frame that the data was collected in was from 1978 to 2020. As seen in the graphic, the borehole data generally shows a very high correlation. We took the average of permafrost borehole temperatures in our data regression model. Permafrost values are left skewed with more data on the left tail, as permafrost values are always lower than zero. We took a log transformation to transform the skewed data into a more normal distribution. Instead of a typical log transformation, we slightly adjusted the formula to adjust for the negative permafrost temperatures, since logarithms have a domain of positive numbers. Thus, we multiplied the temperature inside the log by -1 to make it positive, then multiplied it again by -1 outside the logarithm to preserve the sign of the temperatures and increasing trend. There are many GHGs in Earth's atmosphere that affect our climate. The top three most significant greenhouse gases are carbon dioxide, methane, and nitrous oxide, which account for 98% of the greenhouse gases in Earth's atmosphere. Additionally, researchers found that melting permafrost releases CO2 and CH4 into the atmosphere, creating a positive feedback loop between the climate and thawing permafrost. Thus, CO2, CH4, and N2O were selected because of their significance. From the greenhouse gas emission data, a high correlation, greater than 0.7, between all three gases was observed. As these gases are not independent of each other, a composite score was created. The composite score formula can be observed on the right side of the slide. As you can see, the emission data was first standardized because it mitigated the issue of different units, then multiplied by the GWP value, which determines how much of an effect a greenhouse gas has on Earth's climate. This flowchart depicts the entire process of how our model predicts permafrost temperatures. We already covered the first two steps of data collection and processing, so we can move on to step 3. With the process data, we plug it into a linear regression model to fit a trend line. To predict future permafrost temperatures, a composite score was calculated from the projected GHG emissions data based on the selected SSP pathways and inputted into the model. This resulted in permafrost temperature predictions up to the year 2100, guided by the three SSP pathways. It outlines three temperature predictions for the three SSPs with a 95% confidence interval. The fitted regression line is highly significant, with a p-value smaller than 0.01. From the data, we observed that on average, methane emissions increased by over 100 megatons of CO2 equivalent annually. In our model, this translates to roughly a 5-unit increase in composite score. In turn, it results in a 0.13 increase in permafrost temperature. We also noticed that N2O emissions increased by over 23,000 megatons of CO2 equivalent annually. This translates to more than a 150-unit increase in the composite score, resulting in a 3.8 increase in permafrost temperature. To choose what SSP scenarios we would use for predictions, we decided to pick the scenarios with a high probability of occurring. This would be the most useful and relevant data, as our future approaches to climate change are still uncertain. New policies could be implemented any day. Notably, researchers believe that our world's current emissions put us in the SSP 245 to SSP 585 category. So, they were selected to be included in our study. However, we also want to include a more optimistic scenario that is still achievable if action is taken. Thus, SSP 126 was selected to provide comparisons and a more holistic approach. Depending on the SSP scenario we take after, our model predicts that permafrost temperatures will vary. The blue dots on the left are historical permafrost temperature data. The lines on the right show the model's predictions for future permafrost temperatures. The lighter colors represent the 95% confidence interval band. In the best case scenario, SSP 126, sustainability is prioritized. Carbon dioxide emissions rapidly decrease to net zero after 2050, eventually producing negative net emissions. Other greenhouse gases follow afterwards. Temperatures decrease to negative 4.5 degrees Celsius in 2100. This corresponds with the green line on the chart. SSP 245 corresponds with the yellow line on the chart. Here, our emissions continue similar to today's world. Greenhouse gas emissions do eventually reach net zero, but only after year 2100. Permafrost temperatures reach a high of negative 2.9 degrees Celsius, and temperatures fall a little, with a temperature of negative 4.1 degrees Celsius by year 2100. A 7% increase in temperature can be observed when compared to the year 2000. SSP 585 corresponds with the red line on the chart. This is the worst case scenario where fossil fuel use is continued, with permafrost temperatures rising to around negative 2.5 degrees Celsius. Around 2090, temperatures slightly decrease, but the graph is overall an upward trend. In this scenario, a 36% increase in temperature can be observed compared to the year 2000.
The key takeaways from the study are: number one, increased GHG emissions means increased housing safety risks, especially for those living in permafrost areas. Two, the future of housing in permafrost areas depends on the action we take against climate change and GHG emissions. Three, in the best case scenario, GHG emission trends would follow that of SSP1 2.6. This would result in a decrease of permafrost temperatures, improving housing safety and equity. Four, in the worst case scenario, GHG emissions would not be controlled. Emissions would follow that of SSP5 8.5, and permafrost would continue to thaw.
Before deciding housing locations, areas with prevalent permafrost should be dismissed. However, this solution will not apply to those already living on permafrost who are already facing the safety risks. Our last resort is community relocation, as it is both expensive and disrupts a community. Thus, to combat the issue of thawing permafrost, we propose a few counteractive measures. 1. Reducing the root cause, warming temperatures. This can be done by being more environmentally aware and producing less emissions. We can set forth new policies and place a larger significance on sustainability and the environment. 2. Cooling the ground. Technologies such as thermosiphons have been developed to lower ground temperatures, thus keeping the permafrost frozen for longer. 3. Continuing off the previous point, more technologies can be developed and improved both for cooling the ground and making houses more resilient to thawing permafrost. For example, many communities have already begun to build raised houses, which allows the ground to stay cooler while distancing the structure from the thawing permafrost.
In the future, there are a plethora of related topics for other researchers to study. This includes 1. Optimal housing locations in the extreme north and south. Researchers could optimize areas with the least amount of permafrost and risk of permafrost melting to find the safest areas for construction. 2. Solutions to issues that thawing permafrost presents. Researchers could develop methods to prevent permafrost-caused landslides, housing foundation collapses, and more. 3. Researchers could also collect more data and use more in-depth data sets to find the most promising solutions. 4. Finally, researchers can aim to optimize crop production while minimizing GHG emissions. They can study different methods and techniques that promote sustainable practices and prevent climate change.
We would like to acknowledge STEM Fellowship for providing us with the opportunity to compete in this challenge.
Thank you for listening. You can read more about our paper on the STEM Fellowship Big Data Challenge 2023 finalists website.